talking about representation. Oh, great. Thank you. So we spent the first two lectures talking about representation rings, and there I went into some more detail how restrictions, transfers, power operations, and character maps all interact. And then we did a lecture on Burnside rings last, in which I explained the ways in which Burnside rings behave differently from representation rings. And here we're moving to a third example, which is the example of the Morava E theories. And again, my primary goal is to explain some of the ways in which Morava E theory behaves differently from those other two examples, um, but also to try and provide some intuition for what Morava E theory is and what it sees about finite groups. So how it behaves like a representation ring. And I think the place to start here is first by thinking about p-adic K theory and understanding how it relates to representation rings and equivariant K theory. So I'm going to do a little section here at the beginning called p-adic K theory. And so to get things started here, so let's let Ku sub p be the p completion of the complex K theory spectrum, which means the localization at the mod p Moore spectrum. That's what that means. Not important. Um, then, uh, then I want to relate representation rings and p-adic K theory, and there's something in the middle. So here's the representation ring of G for some finite group G. This admits a map, a ring map, to the complex K theory of BG, the classifying space of G. And complex K theory maps to its P completion. And so this admits a map to the P complete K theory of BG. And I want to think about these maps. So what's this first map? So let's just say what this first map does. So if I've got a G representation V, then I can think about this as a G bundle over the point, where the point has a trivial G action. And so I can pull back. The classical way to say what this is doing is that I take V over a point and I pull back to EG mapping to a point. And this gives me a vector bundle EG times V over EG. And now there's a free G action on both of these things, and I can take the quotient by it. And this gives me a vector bundle EG times over GV over BG. And that's how this map right here is defined. A more modern way to say what's going on is that I just take G to V and I take the homotopy orbits for the G action. Uh, and uh, and then this map here comes from just P completion, the map to the P completion. And this middle ring was analyzed by Atiyah, and in the case of a G space, Atiyah and Siegel. And Atiyah proved a theorem about this thing. So he proved that it could be described in terms of the representation ring. This is the completion of the representation ring of G at the augmentation ideal. So this is the kernel of the dimension map from Ru of G to Z, otherwise known as restriction to the trivial group. Uh, and one thing to note about this is that this is not a module over the p-adic integers. It really just has an underlying abelian group, and it's very poorly behaved as a Z module. So poorly behaved as a Z module. And we often want things to be well behaved as a module over the base in order to get character theory to work right? These representation rings were free Z modules. This is not a free Z module, and it's just enormous because of the completion that's there. But there's a fix to that, and the fix is to work with p-adic K theory rather than K theory. And I learned these results from Strickland. I'm not sure where they go back to. They could go back to Adams, but it turns out that the p-adic K theory of BG admits a similar interpretation. So this is the completion of the representation ring of G at the ideal P plus the augmentation ideal. And that doesn't sound all that helpful until you learn yet another description of this thing, which I learned about in Strickland's Chern approximations paper. This is what you get by taking the representation ring of G, modding out by a certain ideal, and then base changing to the p-adic integers. So what's this ideal J? So this ideal J is the kernel of the restriction map from the representation ring of G to the representation ring of any CeLO P subgroup. Um, and this is a restriction. And this tells us, so RU of G mod J, G is G is an arbitrary finite group. RU of G mod J is exactly the image of this restriction map. And so it's a subgroup of RU of S, which is a free abelian group. So it's a free abelian group. And so this is a free abelian group, and I'm just base changing to the p-adic integers. And so I end up with a free ZP module. So this is a free ZP module. And that's an indicator that we've sort of found the right thing. In fact, we can say exactly what its rank is. So the rank as a ZP module of the p-adic K-theory of BG turns out to be um, uh, uh, the order of GP mod conj, where GP is the set of p power order elements in G. And there's another way to say what this is. It's the set that's going to be useful. It's the set of continuous maps from the p-adic integers into G. So the set of abelian group maps from Z into G is just G again, right? I just need to choose a generator of Z to get a bijection of that sort. A continuous map from ZP to G has to factor through Z mod P to the K for some K because G is a finite discrete group. And so we see that this exactly picks out the elements of G that are of order P to the K for some K. And G acts on the set by conjugation. And so I can take conjugacy classes of P power order elements in G, and that's exactly what the rank of the p-adic K-theory of BG is. Let's just do an example. So here's two examples just to help process what's going on here. So first, if I take the p-adic K-theory of B Z mod P to the K, that's a P group, so the J is trivial. J is the zero ideal. And so this is just ZP adjoin X mod X to the P to the K minus 1 using our previous calculations of the representation rings of cyclic groups a few lectures ago. And on the other hand, if I take the p-adic K-theory of BH, where P does not divide the order of H, then this is just ZP. So from the perspective of p-adic K-theory, BH is equivalent to a point. Okay. And I want to say one more thing about p-adic K-theory, which is that there's a really nice character theory for p-adic K-theory due to atoms. You can read about it in Maps Between Classifying Spaces 2, or something like that. And he constructs a character map from the p-adic K-theory of BG to a ring of class functions that I'm going to call CLP, G, and the coefficients here. Like one of the tricks in constructing these character maps is trying to figure out what the coefficients are supposed to be. And in this case, it's the p-adic rationals adjoin all p to the kth roots of unity as k varies. And this ring is the ring of functions from GP mod conj into QP adjoin mu p infinity. And this is constructed in the following way. So what do I need to do? Well, if I have some map alpha from ZP to G, picking out an element of p power order, then what we need is a map from the p-adic K-theory of BG to QP adjoin mu p infinity to the coefficients, depending on alpha. And it's not so hard to do. This factors through z mod p to the k for some k, and I'm going to call this resulting map alpha again. And I'm just going to apply p-adic K theory to alpha. So I get a map from, I didn't use my notation. I get a map from KU naught of BG to the p-adic K theory of B z mod p to the k. And we just said what that is. So that's isomorphic to the p-adic integers adjoin x mod x to the p to the k minus 1. But this admits a surjection onto zp adjoin x mod the p to the k cyclotomic polynomial, which is just adjoining a primitive p to the kth root of unity. And now that embeds in QP adjoin mu p infinity. And there you go. This is where did alpha fit in? Well, alpha fit in right here. It's alpha star is what's there. And this is how this character map is constructed. And in fact, you can construct the character map for representation rings exactly like this. It's not how I did it. But if you do it this way, you see this thing that I said several lectures ago, which is that the character map is a kind of restriction. And we see that indeed, in this definition, there's a restriction that happens here. Okay. So Adams proved that this is an injective ring map, and it's an isomorphism after base change to QP adjoin mu p infinity. So the kind of thing that you would expect. Are there any questions about p-adic K theory? I'm done with p-adic K theory, and I'm going to move on to Rabi E theory. Okay. So now I have a challenge. What's that?
I have a question. Could you expand more? We could compute the p-complete K theory of the classifying space of the p-adic is actually the QP at the root of I mean the map from the p-adic to G, the alpha is induced by the apply the classifying space, then you apply the KU.
Yeah.
Can you explain a little bit about the target QP actually is the KU cohomology of the classifying space of the p-adic, right?
Can you say it again?
Is this right? The target of this QP at the
Yeah.
root of the unit is actually the KU cohomology of the classifying space of the p-adic integer, right?
No. It's not because there's this is not a primitive. This is not a primitive root of unity here in this case. You gotta be a little bit careful about these things. It's important to quotient further.
Oh, okay, I see. Thanks.
There is a statement like that that you can make, but you got to mod out by a certain ideal that you can define topologically. I'll say something about that in the E-theory case. Okay, so now we have a challenge, which is to talk about what is Morava E-theory in a few minutes. And the real reason this is a challenge, a lot of the ideas aren't that hard, but there's a lot of algebra geometric language that is more or less required to carefully say what's going on. Uh, and so I'm going to try and talk about the parts of that that are the most important, and we'll see how it goes. So first of all, Morava E-theory is determined by what is by a very simple algebraic gadget called a formal group law over a perfect field of characteristic P of height n. So what the heck is that? So let's start there. What are we doing? So let's let K be a perfect field of characteristic P. Perfect just means that the Frobenius is an isomorphism. And let's let gamma over K be a height n formal group law over K. So what the heck is that? So that's a power series that I'm in two variables that I'm going to denote x plus sub gamma y. So this is a power series in K double brackets x comma y that satisfies some group law axioms. Um, and these are that x plus gamma is 0 is x. Associativity, which is that x plus gamma y plus gamma z, if I parenthesize this way, is the same as x plus gamma y plus gamma z. And commutativity, which is that x plus gamma y is y plus gamma x. And then I said height n, and height n is, for our purposes today, just means that if I add x to itself p times using the group law structure here, so this is just x plus gamma gamma x p times, then this is x to the p to the n plus stuff. And the example to have in mind, which we'll go into in a little bit more detail in a bit, is x plus gm hat y, which is x plus y plus xy. So you can check that this is a height 1 formal group law. And we can take this over FP if we want. Okay, so it just turns out that there's tons of these things. There's tons. Um, uh, and uh, uh, and it turns out that the choice of such a thing determines something in stable homotopy theory. So this data determines a K of n local E infinity ring. I'll write spectrum. E, which you could write E sub n, or you could write E of gamma comma K. It's pretty common to write E sub n and just let gamma, assume there's some gamma out there, with even periodic homotopy groups. And I'm going to say what they are. So they are, so pi star E is isomorphic to the p typical vectors on K. This is not a canonical isomorphism. This is just an isomorphism. Join U1 up to U sub n minus 1. adjoin beta plus or minus, where the degree of beta is 2. In particular, well, let me first make a comment here. So first of all, this p-typical vectors of K, don't worry about it too much if you haven't seen it before. In the case that K is FP, W of FP is just the p-adic integers. And for our purposes today, it suffices to think about that as just the p-adic integers. And pi naught of E is canonically a special ring that shows up. It's called the Lubin-Tate ring, which is a ring from arithmetic geometry. And it's a complete local ring. It's exactly this part of the coefficients. It's a complete local ring. The p-typical vectors on K is also a complete local ring with maximal ideal given by P and whose quotient is K. Um, and uh, and this Lubin-Tate ring is the thing. So here's just some words, which carries the universal deformation of this fixed gamma over K. That's a little k. And all of this together is kind of a big theorem. And I'm going to just attach the names Gorse, Hawkins, and Miller to this. But there are more things going on behind the scenes, going back all the way to Landweber and Morava. And in fact, Gorse, Hawkins, and Miller do much more than just specifying an E-infinity ring spectrum like this. They actually identify an extremely rigid portion of the category of E-infinity ring spectra, the infinity category of E-infinity ring spectra. But this is what we need today. And so here's some statement. And what are the consequences for us? Because we're interested in a very particular thing, which is this global algebra stuff. And so the consequences for us are the following. So since E is a spectrum, well, the associated cohomology theory determines a global Mackey-functor. When I consider its values on classifying spaces of finite groups. Since E is a homotopy commutative ring spectrum, well, the associated cohomology theory actually determines a global Green functor. When I consider its values on finite groups. So I get commutative rings out when I consider the value on BG. And I have Frobenius reciprocity, and the restriction maps have to be ring maps. But more, since E is an E-infinity ring spectrum, well, we get a global power functor when I consider the values on finite groups. So it has even more structure, but there's still even more. So since E is K of n local, we get transfers along surjections. And so the value of E on finite groups has all of the structure that we saw in these other two examples. I want to expand on these last two. So let's talk about the power operations. And let's talk about the transfers, because in this case, these are coming from a different source than in the previous two cases. In the previous two cases, the existence of these two things really followed from the fact that we had some kind of geometric or combinatorial objects that gave rise to our rings. And that is just not what's going on in this theorem. Um, so where do the power operations come from? Well, the power operations come from the usual way power operations come about. If in given an E infinity ring. So if I have a homotopy class of maps from BG to E, so E is a spectrum, BG is a space, I'm always secretly applying a sigma infinity plus whenever I put a space in. Then I can take the nth power of this. That puts a times m here and a smash m here. And this map is sigma m equivariant, so I can take the homotopy orbits for it. And the thing on the left, where I take BG to the M and I take the sigma M homotopy orbits, this is actually BG Reith sigma M. It's the classifying space of the Reith product. And the thing on the right, because we have this E infinity ring structure, comes equipped with a map, which is a multiplication map, back down to E. And so what have we done here? Well, we've produced a map from the E cohomology of BG to the E cohomology of BG Reith sigma M. And that's our power operation. So this is PM. So that's where the power operation comes from. And then what about the transfers along surjections? So I'll call this K of n local transfers. Um, so for this, I need to introduce completed E homology. So let's let E lower naught hat of BG be pi naught of the K of n localization of E smash BG. So this is like the pi naught of E smash BG would just be the E homology of BG, but there's an extra localization to force everything to be K of n local. And there's a theorem, which is K of n local Tate vanishing. If you know what it is, then if you have some idea what it is, then that's the thing that's leading to the following fact. But if you don't worry about it. This is a theorem of Greenlee, Sadovsky, Kuhn, and also Strickland was involved in thinking about these things as transfer maps. K of n local Tate vanishing tells us that there's a canonical isomorphism between the E cohomology of BG and the completed E homology of BG. And so that's a really amazing fact. And it tells us that if we've been given some map of finite groups, H to G, that's not necessarily injective. Well, what can I do? Well, I can define the transfer along phi to be, well, I got to start with the E cohomology of BH, but then I'm going to apply this canonical isomorphism to get over to the E homology of BH. And then I can just take the completed E homology of phi to get to the completed E homology of BG, and then I can go back along my canonical isomorphism again to get to the E cohomology of BG. And there we go. We just produced, using this canonical isomorphism, a wrong way transfer map. And that is the transfer along a surjection in this situation. Okay, so I've talked about power operations and transfers here, and I'm going to have to start saying a few things about algebraic geometry. But before I do that, are there any questions? Does this make some sense? So further, since E is even periodic, we have a complete understanding of the cohomology of CP infinity or BS1. This is just the coefficients, double brackets, X. And this just follows from the collapse of the Tia-Herzberg spectral sequence in this case. And this thing is, is the ring of functions on a formal group. And this is always true if I have an even periodic cohomology theory. But something special happens here because E naught is a complete local ring. This thing, E naught double brackets X, is itself a complete local ring. I can take the maximal ideal of E naught and add X to it to get the maximal ideal of E naught double brackets X. This isomorphism here, this is non-canonical. And it's better to think about the left-hand side as the ring of functions on the formal group. And it just happens to be isomorphic to that. So what is this thing? What's that mean? Well, it means that there's an algebra geometric object, which I'll call spoof instead of spec because we're in formal schemes, which is E naught of BS1. And I would denote this thing G sub E. It's the formal group associated to E, which is a functor from complete local E naught algebras to abelian groups that takes a complete local E naught algebra, R comma M sub R, to an abelian group structure on M sub R comma 0, where the addition comes from the addition in this formal group. It's not the normal addition on the maximal ideal. It's addition coming from the fact, whoa, that was not what I intended to do. It's addition coming from the fact that E naught of BS1 has a co-multiplication induced by the multiplication map on S1. So this is, in this situation, thinking about this thing as a functor like this is a good idea. You win stuff. You win good stuff from that. Okay, I want to do an example. So in this case of K equals FP, and the formal group law is X plus Y plus XY, which is the formal multiplicative group law. In this case, the P series begins with X to the P. You can check this. It is important that we're working characteristic P for that to be true. And in this case, the Morava E theory associated to this is exactly p-adic K theory. So p-adic K theory is an example of a Morava E theory, but chromatic homotopy theory furnishes us with all of these generalizations of p-adic K theory. And these turn out to be pretty well-behaved cohomology theories, and also the main way we have to access the K of n local category. These Morava E theories play the role of the algebraic closure of Q for chromatic homotopy theory. Okay, right. So we need one more thing. Got to figure out how to tell this story right. So I've said something about what the cohomology of CP infinity is, but the thing that's really important to us, going back to that character map that Adams constructed for p-adic K theory, is to understand what the cohomology of cyclic groups is. And it turns out that the e-cohomology of Z mod P to the K has a nice algebra geometric interpretation as well. It's the P to the K torsion inside of the formal group. So there's a functor, there's a subfunctor of GE, which also lands in abelian groups, but instead of giving us MR, it just takes the elements in MR for which P times them using this addition is uh is zero. And that's exactly the P to the K torsion in the formal group. And that's another well-behaved algebrogeometric object. And we can say what it is in coordinates. This is spoof of E naught, double brackets X, mod the P to the K series for this, for, for some choice of coordinate and thus some formal group law associated to GE. So this again,
Uh,
this is a non-canonical isomorphism, but this is canonical actually. Yeah. Yeah.
is this E parentheses GM hat FP, is that some cohomology theory that you construct using the Gorse-Hopkins-Miller theorem or something?
Wait. This?
Further left and then up.
This.
Yeah. What is that?
I'm using, sorry, yeah. I'm using
What's
a
that?
ton of notation and it's not going to get better, for which I apologize. I am using this notation right here.
Gotcha. Okay, cool.
Yeah, it's not going to get better. It's going to get worse. Um, Much worse. Uh, yeah. Uh, so the idea for why this is true, I shouldn't write anything down for time reasons, but the idea for why this is true is because of the a Giesen sequence argument, and it uses the fact that the P to the K series here is not a zero divisor in E naught double brackets X. Okay, I want to talk about character theory for Meravi E theory. So this has a name. This is Hawkins-Kuhn Ravenel character theory. And I'm already very concerned about time. Yeah. Maybe I can do it. So there's a few questions that you have to answer here. And the main one is what's the analog? What's the coefficients? So the analog of Q adjoin mu infinity in this setting is a Q tensor E naught algebra that is called C0, and it's the rationalization of a ring that I call D infinity, which is called the Drinfeld ring at infinite level. And I want to give an idea of what this is. And at some point, I'm just going to have to start skipping large quantities in my notes. Um, so, so there's a thing that I can do. So I can take this P to the K torsion in GE, and I can raise it to the nth power. And a better name for what this is the group scheme of maps from CP to the K to the N into GE. So I'm using CP to the K instead of Z mod P to the K because I'm really thinking about this as a kind of Pontryagin dual of Z mod P to the K. And so there's this scheme of maps from the constant group scheme, which is CP to the K to the N, into the formal group GE. And that's this thing on the left. And this contains a very special subscheme, which is called level. And what level tries to capture, this is not an abelian group scheme anymore. This tries to capture the injective maps. Injective maps from CP to the K to the N into GE. So it turns out injective is not something you're allowed to say for reasons of functoriality. But there is a good approximation to injective and the property that it has is that if I have a subgroup of this discrete thing, I can always take its image in here to get a subgroup of the same size in GE. So like that's a thing that I would hope out to have out of injective maps. It's not true if I have an arbitrary group homomorphism from here to here. If I have a subgroup here, I might get the zero subgroup here. That's very small. But the injective maps have the property that if I have a subgroup here, I get a subgroup of the same size. That's its image here. And just to give some indication of what this might look like. So, so the ring of functions on level CP GE, so it's not with the power to the n there, is E naught double brackets X mod the angle brackets P series of X, where this angle brackets P series is the P series mod X. So I'm saying I want a P torsion point. That's what a map from E naught double brackets X mod the P series would be. I want a P torsion point, but I don't want it to be zero. So that's what it should be like. That's what an injective map should be, right? It should be like, oh, I want a P torsion point, and I don't want it to be zero. And that should be an injective map from CP into GE. And so that's what I've got. So that's a ring that's easy to describe. And this one, the ring of functions on this thing is much harder to describe. It was studied by Drinfeld. It's extremely well behaved. It's a complete local domain. Um, but writing it down in terms of generators and relations is super hard. So so there's a canonical map from level CP to the K to the N into GE to level CP to the K minus 1 to the N into GE. And it's just given by restricting to the P to the K minus 1 torsion inside of the source here, right? It's just restricting to this thing as a subgroup of this thing. And this induces a map on rings of functions the other way. So a map from O level here to O level here. And I can take the co-limit along that map, and that's what D infinity is. So D infinity is the co-limit along over K of O level CP to the K to the N GE. Or if you wanted to try and write this all at once, you might write level CP to the infinity to the N GE. And because the automorphism group of CP to the infinity to the N is GLNZP, and if I have an injection and I precompose with an automorphism, I get another injection. There's an action of GLNZP on this ring. And in fact, the fixed points for this action are the Lubin-Tate ring itself. Okay. And the ring C0 that's going to play the role of our coefficients is Q tensor D infinity, just the rationalization of this ring. So, okay. Are there any questions that I know it's fast and I know I didn't define stuff. Uh, this ring is really interesting. You can read about all this stuff more in my handbook article, for instance, and lots of other places. Strickland's work on subgroups, stuff like this. Is there anything that I can say to clarify something? I know it's confusing. Okay. I want to say one more thing about this thing. So Q tensor E naught of B Z mod P to the K to the N mod a certain ideal is isomorphic to Q tensor O level CP to the K to the N G. And this ideal is the image of the direct sum over all proper subgroups of Z mod P to the K to the N of the transfer from A to Z mod P to the K to the N. So this gives a topological way of thinking about these level structures, at least after rationalization. Okay, we're set up to talk about character theory, actually. So what is going to play the role of conjugacy classes? So let's let G, P, square brackets N be the set of continuous maps from ZP to the N into G mod conj. So what is this? This is conjugacy classes of n tuples of commuting p power order elements inside of G. N tuples of pairwise commuting p power order elements inside of G. And the character map of Hopkins, Kuhn, and Ravenel starts with the ecohomology of BG and lands in a version of class functions that I'll call CLNPG, taking values in this ring C0, which is functions, the ring of functions on GP, on these n tuples of pairwise commuting p power order elements in G are taken up to conjugacy, taking values in C0. And the character map is constructed in the exact same way as Adam's character map. So I have some map from ZP to the N into G, which is alpha, and I want to produce a map from E naught of BG to C0. And what I'm going to do is factor this through Z mod P to the K to the N. I'm going to continue to call this map alpha. I'm going to apply ecohomology to this map. So this gives me a map from the ecohomology of BG to the ecohomology of B Z mod P to the K to the N. And now I can rationalize and mod out by that ideal that I just described. And that's the rationalization of level structures. And so C0 was a colimit, and so this maps to C0. And there it is. That's how the character map is constructed. And the theorem is that first, chi is a ring map. Well, this was a ring map, so this is just true. Normally I say injective here, but it's only injective when E naught of BG is a free E naught module. Okay, I should say torsion free. And we know that that's not necessarily always the case, but for all G that you want to consider, it is the case. And C naught tensor over E naught with chi is an isomorphism. So the character map here becomes an isomorphism after base changing the source. Oops. Whoa. How did I do that? Go back. No, go back. After base changing the source over E naught to C naught. And just as before, there's a gln-zp action instead of a z hat times action. There's a gln-zp action on the target coming from, well, gln-zp acting here and gln-zp acting on C0. And after base change to C0, it's just on the left. And I can take the fixed points and we end up with a map Q tensor chi from the rationalization of the ecohomology of BG. That's an isomorphism into CLNP GC0 GLN CP fixed points. Okay, so that's how character theory goes in this situation. And I have way more that I wanted to say that I'm just not going to be able to say. So I want to get to the punchline reasonably quickly. So first, let me say that you can ask how the power operations and the character maps relate in this situation, just like we did both for the representation ring and for the Burnside ring. And we have a nice formula for this too. This is self-promotion, work of myself with Toby. So we figured out a nice generalization of that formula that's there for both the Burnside ring and for the representation ring that makes sense in the case of E theory. And it also turns out that there's ways to use a theorem of Strickland's that I want to describe right now to build lots of operations on Morava E theory from the total power operation. You can build Adams operations, you can build Hecke operators, and I'm not going to be able to go into all of them in detail, which is what I want to do, but somehow this got away from me. But Strickland proved a theorem that's really useful. He showed that if we let I sub transfer contained in the ecohomology of B sigma M be the image of the transfer maps over I plus J equals M, and with I and J greater than 0, of the transfer from sigma I times sigma J to sigma M. So this is some ideal in the ecohomology of B sigma M. Then E naught of B sigma M mod I transfer is a free E naught module. And this is a ring, and it actually co-represents a very important functor on the formal group. It's canonically isomorphic to the functor that classifies subgroup schemes of order M in the formal group associated to E. And this theorem lets you get a hold of power operations because the composite E naught to E naught of B sigma M to then the quotient is a ring map. And so this is because these are exactly the transfers that we need to kill to get rid of those cross terms in the formula for the power operation on a sum of elements. So this composite right here is a ring map, and work of Ando, Hopkins, and Strickland gave an algebrogeometric interpretation of this ring map. And so this is like the first ring map that you could build out of the total power operation. And so having an algebrogeometric interpretation for both of these sides and for this map allows us to use algebraic geometry to construct operations on Morava E theory. And so what I want to do is go back to that big diagram that I drew um, for representation rings, but now I want to do it in the case of Morava E theory. So I've got the E cohomology of BG. I've got my total power operation. This goes to the E cohomology of BG Reith sigma M. I can pull back along the diagonal. So this goes to the E cohomology of BG times B sigma M. And I can transfer because I have transfers along surjections along the projection from G times sigma M to G. And this brings me back to the E cohomology of BG. And whatever this map is, it deserves to be called the symmetric power, because that's how we construct the symmetric power in the case of representation rings. On the other hand, because the E cohomology of the symmetric group is a free module, this is a result of HKR, which I wanted to get into more, but I don't have time. There's a Kunith isomorphism here. And now I can quotient out by the transfer ideal on this side. So this comes here. And the resulting composite is now a ring map. But it turns out that it's a little tricky compared to the representation ring side to get back down to E naught of BG. When we were considering representation rings, the thing that was here was already the integers, and that is not true in this case. So ideally, you'd like some kind of natural map from here back to E naught. And that turns out to be possible. It's just a little bit trickier. And it's also only really interesting in the case that m is a power of p to the k. And then what there is there's a map, which I'll call one tensor the sum of LAs, whatever that is. And this goes back to E naught of BG. And these LAs that are here are ring maps from E naught of B sigma M mod I transfer to the Drinfeld ring, to D infinity. But they don't land in E naught. They land in D infinity. But the trick is to sum a whole bunch of these ring maps up so that it lands in the invariance for the GLNZP action on D infinity. And so it lands in E naught. So this is a sum of ring maps that goes here. So it's additive, but it's not multiplicative anymore. We lost multiplicativity. And this composite right here is known as T sub p to the k. This is the p to the k Hecke operator. And I'm talking about this because there's a theorem, that's Ganter's thesis, that the sum over m greater than or equal to 0 of the beta m's t to the m is equal to x of the sum k over k greater than or equal to 0 of t sub p to the k over p to the k of t to the p to the k. And so if you're asking what the logarithm of the sum of symmetric powers is in the case of Morava E theory, there's a really nice answer to that question. The correct generalization of the Adams operations to Morava E theory, at least as far as the symmetric powers are concerned, are these Hecke operators. There are Adams operations on Morava E theory, but they're not the thing that has this role with the symmetric powers. It's these Hecke operators that do. And my final lecture tomorrow is going to be trying to understand where these exponential relations come from and produce a more universal exponential relation that gives rise to both the exponential relation that we see in representation rings and the exponential relation that we see here. Okay, I'm going to stop there.
All right, let's thank Nat for the lecture.